standard inner products give us one specific way to measure lengths and angles. But to understand custom geometric systems, we have to look at how we can systematically change these rules of interaction. A form is a generalized function mapping two vectors to a single scalar. The first slot behaves with standard linearity. Scaling the vectors scales the output proportionally. But scaling the second vector pulls out the complex conjugate of that scalar. This is known as sesquilinearity. By combining these two specific rules, forms provide a mathematical framework to define entirely new ways for vectors to interact across complex dimensions. Theorem 1 simplifies this complexity by proving every form on an inner product space corresponds to exactly one unique linear operator. Instead of evaluating an abstract two-variable function, we apply a specific operator, t, to the first vector, and take the standard inner product with the second. T encodes every geometric rule. Every twist, stretch, or rotation is contained within this single transformation. This mapping allows us to apply everything we already know about linear operators, like eigenvalues and spectral theory, directly to the study of forms, without having to develop new tools from scratch. To make this practical for computation, we shift from abstract operators to coordinate matrices. Here, x and y are coordinate matrices, and A represents the form. We build A by testing the form against all basis vectors. If a form is Hermitian, swapping inputs yields the complex conjugate, forcing the matrix to equal its conjugate transpose. If the Hermitian rule requires an output to equal its complex conjugate, what happens when plugging the same vector into both slots? By Theorem 3, it must be real. Evaluating a vector against itself always yields a measurable real-world scalar. When we change our basis, the matrix A transforms using a transition matrix P and its conjugate transpose. If we use a unitary basis, where the conjugate transpose equals the inverse, the form's transformation aligns perfectly with how a linear operator changes basis. This alignment means that if a self-adjoint operator can be diagonalized by a unitary matrix, its associated Hermitian form can be diagonalized by that same basis. This leads to the principal axis theorem. This theorem guarantees that for any Hermitian form, there exists an orthonormal basis where its matrix becomes purely diagonal. Those zeros prove interactions between basis vectors are decoupled. In this coordinate system, the geometry is reduced to its simplest state. While forms begin as abstract generalizations, the principal axis theorem provides the mechanism to entangle them, reducing a custom geometric system to its core diagonalized components. If you want more breakdowns of the proofs in Hoffman and Kunze, subscribe and check out the Linear Algebra playlist. Thanks for watching.